Right, I think we'll begin. So thank you everyone for attending this CAST seminar for today. My name is Nathan Cooper. I'll be facilitating the session. Before I begin, I would like to begin by showing my respect and acknowledging the Eora people who are the traditional custodians of the land of elders past and present on which I'm facilitating this seminar from. And I extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. So for this meeting, I'd like to introduce, well, actually, first I'll start by explaining, for those who haven't attended a CAST seminar before, kind of how this will work. So if you do have, I do encourage questions during the seminar. If you do have any, please type them into the chat. And at the end of today's seminar, which will take between 30 and 40 minutes, we'll hold a 15 or so minute session of Q&A where you'll be able to ask those questions at the end. So today's speaker, I'm proud to announce, is Dr. Giovanni Virgilio, and from the Department of Planning, Industry and Environment at New South Wales. So Giovanni's current research focuses on regional climate modelling with a keen interest in model design and evaluation, climate change adaptation, and projections of future extreme wildfire risk. He also has an interest in air pollution meteorology and has worked on projects investigating the impacts of wildfires and hazard reduction burning on air quality in Sydney. And today he's here to talk about climate resilient planning at local scales, from leveraging real-time observations to next-gen climate modelling. So I'll hand over to Giovanni and yeah, very excited for this.
Thank you very much, Nathan. Thank you for inviting me here and giving me the chance to present some of the research that I've been doing. I'll get straight into it and share my screen and presentation. Okay, is the first slide visible?
Yeah, all good.
Okay, great. So thank you again. I'm going to present an overview of some of the research I've been doing, and really it's research that goes down two different pathways, using observations on the one hand and climate modeling on the other, but ultimately to try to help inform mitigation planning for some of the consequences of climate change, some of the impacts that we're experiencing right now in Australia. So, presentation overview. I'm going to give a very brief rundown of some of the climate change impacts that are being experienced increasingly in Australia and some of the background to those changes. Then I'll talk about using an observations-based approach to investigating the climate change impacts of a specific phenomena that unfortunately is a fire-prone region we have to deal with in Australia. So I'll specifically focus on the black summer wildfires that we experienced recently. And this uses DPIE data and also citizen science data that I helped set up. And then part three, we'll look at how the regional climate modeling being delivered and also being designed at DPIE, and that I'm playing a key role in, is usable for climate change mitigation planning. And hopefully some of that data will be interesting and useful to the members of this audience. So in terms of the climate change science, the basic science, I'm not going to go into this in great detail, but as you'll all be aware, atmospheric CO2 concentrations are increasing very, very rapidly, and they're at unprecedented levels with a really sharp increase since 1950. And that is what is driving the global warming that has led to the Earth increasing by about 1 degree on average since the late 19th century. Now, this is established science, very high quality observational data sets, like those shown in the right-hand plot there. You've got 5 different high-quality observational data sets. They all replicate and track one another very well in terms of the changes that we're experiencing. We've only an upward trend. Obviously, you're getting peaks and troughs throughout the time series on an interannual basis, but it is an increasing trend. Now, in terms of what changes are we seeing in Australia, what are the changes that is the focus of the data that I'm preparing in my work is hopefully useful to managing and dealing with these changes. Well, we're getting about 1.14 degree change across Australia, but actually the temperature in New South Wales is currently rising a lot faster than other states. So 1.68 degrees in 2018. And that's relative to a historical average of 1961 to 1990. So we're looking at these epochs and comparing. So a warming climate, especially in New South Wales. Rainfall on an interannual basis is notoriously variable in New South Wales and Australia as a whole, but we're seeing reduced cool season rainfall, particularly over the past couple of decades. So all of these changes, unfortunately, will lead to a changing profile for extreme events in the future in Australia. So this graphic from King et al. Shows you different types of extreme events down the leftmost column there, and then how the chance of those events per year changes relative to the current world, 1.5 degree world and a 2 degree world. And just focusing on the angry summer of 2012, 2013. In the current world, we've got a chance of about 44% per year. In a 1.5 degree world, it rises to 57%. And then in a 2 degree world, it increases to 77%. So just that half a degree change is really increasing the chance of that event occurring per year. And that's really just to underscore the sorts of problems that we're likely to face, but more importantly, why it's really important that we keep warming to the target of 1.5 degrees. It's a critical target to hit to. So those changes mean a varied risk profile right across the huge continent that we live on. So everything from severe tropical cyclones to widespread coral bleaching in the Great Barrier Reef, to increased storm intensity for some sorts of storms, and then heat waves and bushfires, particularly in southeastern Australia. And it's bushfires that I'm going to focus on, really like a case study, as one of the events that are strongly associated with the changing climate. Now, we're a fire-prone region. We frequently experience severe wildfires, but unfortunately, the frequency of those wildfires is expected to increase with climate change. So work that I've done and Dowdy's done, amongst others, is showing that we're getting more severe wildfires, but also a forward extension and lengthening of the fire season and occurring much earlier into spring than we're used to seeing. It's also happening elsewhere in the world. So in North America already, there is evidence that the severe wildfire frequency is increasing. Now, for Australia in particular, there's a lot of urbanization going on along the bush-urban transition. So that increases the exposure of the population to the risks associated with wildfires. And also in Australia, actually, the cumulative number of pilot cumulonimbus wildfires, which are particularly extreme fires, is actually increasing year on year. So we've got this problem that is unfortunately going to become more common. So in terms of studying these sorts of phenomena, we've got essentially two broad approaches. We can use observations to look at the past and present climate, or we can use numerical models. So this seminar is going to look at both approaches, but we're going to start by looking at observations. So this is the first part of the research that I'm going to present, and it's looking at using mid-cost and regulatory grade sensors that produce observations to study the air quality impacts of the Black Summer wildfires on Australian schools. So a big part of this project is a citizen science project that I led with colleagues at UNSW when I worked there to place meteorology and air quality sensors in public schools across Sydney. Now, we actually started this project in 2018, and it took a long time to get the network up and running and stable and presenting reliable data so that we could use it for research purposes. But it's not just about collecting research-grade data in locations across Sydney. It's really about wanting to boost kids' interest and involvement in STEM subjects as well, because they get to use the research-grade data from the meteorology and air quality sensors that we've placed around Sydney in their schools in curriculum-aligned activities in their classrooms. And really, that's to improve community engagement and agency in climatology in the locations where people live. As we'll see in a minute, DPIE has got an excellent observational network, but it cannot be everywhere. So we've deliberately focused placing these network sensors, R1s from SWAC, in areas that don't have current coverage, and in the schools where kids are spending a lot of their time. And that data is now freely available. We have a website where you can get the data and see real-time updates, but also we're going to publish it on Turn very, very soon. In terms of the study area then, well, we've got the Greater Sydney region, and this map shows you the DPIE network that we use for this data, the regulatory grade data, and also the SWAC network. And the red squares are the DPIE stations. So we've got 19 very high quality stations collecting air quality meteorology data with data going back over a decade from some of these stations. So you can see a really broad coverage there across Sydney. And the SWAC network is new. This is the citizen science network that we've set up. That's represented by the yellow circles and the white circles. And you can see that we've deliberately focused on areas that are not covered by DPIE sensors, and in particular areas that are on the urban bush fringe. So if you look at Luddenham out in the very west of the map there, that's an area of big urban change where they're building a new airport. Now the white circles are meteorology only, by the way, I should say. And we're also focusing on a lot of results today, but we'll primarily use Glenorrhea in the SWAC network as an example. So that's right up in the north there. You can see that circle there. Now, just a note about SWAC and DPIE sensors, because they are very different levels of technology. The SWAC sensors up on the left there are mid-range sensors. So they're by solar equipment, and they use different technology to do things like estimate pollution. So that's estimated via laser particle counters. And as you can see, they are sited following guidelines for urban areas. So they're 2 meters above ground, they're near trees, they're near buildings. So very different siting standards compared to DPIE, which you can see you've got a proper regulatory grade air quality monitoring station and meteorology station. They use different technology to estimate pollutants of fine particulates. They use beat attenuation monitors, very, very accurate. And also siting standards are different. You can see it's far from trees and buildings, 10 meters above ground. So these locational differences are important to bear in mind when we're going to interpret results in a bit. So in terms of some of the research aims for looking at the air quality impacts of Black Summer, we need to evaluate the SWAC sensor observations relative to DPIE data to make sure they're actually reliable. Then really provide a detailed spatial temporal quantification of the air pollution impacts of the wildfires at the SWAC and government stations during this period of time. And ultimately, that's to look at how concurrent local and synoptic scale meteorology modulated those air pollution impacts. And also to look at how that can feed into early warning systems and mitigation of these impacts. Now, there's a lot of results that were produced in this work. We're just going to look at a sample today, but this work is in press in atmospheric environment if you're interested in taking a look. In terms of validating the SWAC sensors, overall, there's fairly close correspondence for meteorology variables. There's slightly greater divergence of air quality variables. So we're comparing the SWAC sensors with their closest DPIE equivalent using linear regression. Now, we did co-locate a SWAC sensor with a DPIE sensor. That was the only one that suffered a major technical outage. So we had to go for this next best option of just looking at the nearest sited stations. So here we're comparing SWAC Glenorrhea with DPIE Rouse Hill. So there's a good 12, 15 kilometers difference between these two sites. There are geographic differences, but you can see the correspondence of temperature is really pretty nice. For PM 2.5 in the middle here, it's not too bad. It's an R squared of about 0.6. And that's noting, the big distance between the two, but they're still able to capture similar pollution events, as we'll see in a little bit. Performance for gases is actually pretty good, given the distance between stations. So we've got an R squared of about 0.8 here. We also looked at the monthly cycle and root mean square error for PM 2.5. So it's really interesting here. Again, we're comparing multiple SWAC sensors against their closest DPIE equivalents. You've got this strong seasonal cycle here, really peaking the RMSE, very, getting much higher as you go into the summer months when you have most of the wildfires, when there's a lot of pollution in the air. So in terms of trying to understand what during Black Summer, September 2019 to May, January 2020, but we go on into May to make a comparison. This is just a simple approach looking at monthly pollution roses to show how the wind directions contribute most to overall PM 2.5 before, during, and after Black Summer. And you can see September, October, really you've got pretty good air quality, but you get to November, December, January, and bang, you're getting this very strong pollution signal, which is traceable to the fires. Interestingly, in November, you've got quite a broad range of different directions, wind directions that contribute to the air pollution signal there. Whereas in December and January, it's primarily northwesterly and southeasterly winds that are affecting PM 2.5 at SWAC Glenorrhea. And then we get into February, March, and the subsequent months when the fires are subdued, extinguished, and we've got the usual situation of pretty good air quality at this location right up in the northwest of Sydney. Now, to look at the hourly variation in PM 2.5 concentrations at 6 SWAC sites during the month of November in Black Summer. You've got the 6 sites stacked here vertically, and we've got the hourly variation in PM 2.5 time series plotted relative to references. We've got the regulatory guideline, which is a 24 average, but you can see in the black dashed line there. And then we've got the historical mean of all hourly PM 2.5 observations. And what you can see is very clear spikes in PM 2.5 are being registered at all the locations in the SWAC network, and they are reverberating across the very big area of Sydney that is covered here. So for example, focusing on the 13th of November, you can see this very sharp peak in PM 2.5 is registering right across the network and going way above the regulatory guideline. And often these peaks lasted for about 2 to 8 hours, varying from day to day. Now, comparing that with the DPIE sites to make the comparison with the regulatory grade network, same month, overall, you're seeing a very, very similar situation. And interesting as well, or a good thing from our perspective, is that the events that are being recorded by the SWAC sensors are being also registered by DPIE and vice versa. So essentially, the lower grade sensors are capable of detecting these events. The timing and the duration varies a bit, as you'd expect, because of the locations being different. But overall, you're getting this correspondence between the 2 different networks. Now, I mentioned we've got these citywide impacts of bad air quality events on specific days, but actually looking at the detail, it's a bit more nuanced than that. This is 20-minute variation in PM 2.5, again at each SWAC site on a specific day, the 26th of November 2019, which was a pretty bad day air quality-wise. So essentially, you can see the peak of the PM 2.5 is lagged as you look at the different sites. It hits first at Luddenham in the far southwest, which is about 45 kilometers west of the CBD. Then it hits Leppington, which is a little bit nearer to the CBD. Then Cornell at the southwest. Then UNSW in the eastern suburbs, before tracking round to the north, Glenora, and then the very far northeast coastal station of Brookvale. So you've got this sort of like almost wave-like impact as the air pollution is transported across Sydney and impacting each station at a slightly different time. But still, the timing of these events is important to note, particularly when we tally it back to the concurrent meteorology of the day. So to just dwell on the theme of the 20-minute time series and also the meteorology concurrent with the pollution impacts, we're looking here at the 20-minute time series again on the 26th, and we've got the PM 2.5 in the red time series there, in the bottom of the top left panel, and then we've got the simultaneous changes in air pressure, humidity, wind speed, and temperature, again at SWAC Glenora. And if you focus on the PM 2.5, you've got these 2 sharp peaks in the concentration, one at 7 in the morning, and another that starts at about 3 o'clock in the afternoon and lasts right through to about 10 o'clock. The little black arrows are the wind speed, wind direction superimposed at each time step. And then you've got the changes in meteorology. And you can see that a very sharp reduction in air pressure throughout the entire day lasts right until the onset of the big pollution event at about 3 o'clock. And then as that pollution event really kicks off and lasts for a while, you're getting this very rapid increase in air pressure that stays high. You've also got a very marked reduction in humidity throughout the entirety of that day. We'll talk about that in a minute, but very, very low humidity whilst you've got this bad air quality event happening. Wind speed is quite variable in the green line, and then temperature again is pretty high, as you would expect it to be in the middle of the day, but you've got again this drop here. So interestingly, these 20-minute by 20-minute variations in pollution and meteorology variables actually are reflected in the synoptic behavior of the day. So along the bottom here, we have mean sea level pressure analyses on BOM, and they kind of reflect the changes we're seeing in the pollution and the meteorology, as I've said. If we look at the leftmost plot at 5 in the morning, we essentially have a westerly flow here on the western flank of a Tasman Sea high. So we've got this very warm, dry air coming in from the inland regions over the Sydney airshed, which are classic conditions associated with bushfire weather. However, we go to the middle plot a little bit later at 11 a.m. Now we've got a cold front passing, moving right over Sydney. Now at this point, you're getting freshening winds, you're getting a reduction in air pressure, and freshening winds coming in from the northwest. You're getting this sharp reduction in temperature around about that time, but wind direction is changing, coming in from northwest. Now, afterwards, at about 5 o'clock in the right bottom panel, that cold front has passed. Now you're getting a rapid increase in pressure again, and you're also getting the wind changing round to be a southwesterly direction. So linking all of those changes and looking at high split to compute back trajectories for where the air pollution is likely to come, we can see that looking up at the map, at the start of the day at about 7 o'clock, that fire up to the northwest of Swat-Glenori is contributing most of the pollution at that particular time. And then later on in the day, when we're getting the pronounced pollution events starting at about 3 o'clock and the southwesterly winds, it's mainly the fire actually at point 2. And later on in the day, and going into the next day, the fire right down in the south coast there is impacting air quality in Swat-Glenori. So all of that apparent covariation between local scale meteorology may wonder, to what extent are synoptic weather patterns modulating the air pollution impacts of black summer. So we looked at a warm month synoptic catalog generated by my colleague at DPIE, Virgilio, and that basically identifies different cyclones and anticyclones, troughs and ridges, and categorizes them into 12 different types that you can see in the left graphic there. And so just to start very simply, we produced pollution rises conditioned by those different synoptic classes. So instead of conditioning by month, we're just conditioning by synoptic types here. And you can see there in the right graphic, you can clearly see the different types that contribute most to the PM2.5 signal. So it's really mainly types 5, 6, 7, and 12. The other synoptic types are not really contributing to the pollution signal very much at Swat-Glenori. Now, types 5 to 7 are characterized by prefrontal troughs, except for 12, which is anticyclonic. And that was a pattern that we found repeated time and again for the different SWAC school sites and also for the DPIE sites when we compared those. Other different types of synoptic class, like type 9, are predominantly associated with good air quality. And it was very interesting to see that result replicated again and again. Now, we looked at a statistical link between these patterns later on, and I will get to that in a minute. But in terms of dwelling on the synoptic systems a little bit more, it raised the question, was there something peculiar going on about the synoptic weather patterns during black summer? So we looked at a 20-year historical record going right back to 2001 and looking at the frequencies of the different synoptic systems and essentially the monthly variations in the daily frequencies of those different synoptic types. And the take-home message is they were broadly different between the black summer period and the corresponding periods going right back 20 years. So it's not that the synoptic patterns were different, it's just that certain synoptic types are strongly associated with bad air quality when you have a lot of wildfires. Now, to take that one step further and apply a statistical modeling approach, we looked at the meteorological covariates of elevated PM2.5, focusing on SWAC sites, but also looking at DPIE. Here we're looking at Swat-Glenori, though, just as an example. And for this, we use generalized additive models. So those are very effective at capturing the non-linear influences that you can often get on PM2.5 concentrations. And you can see we've got the different predictors here: relative humidity, maximum temperature, air pressure, so on and so on. I can't really dwell on them all into time, but you can see across the board, we've got these very complex non-linear relations that also are indicative of what the meteorology is actually doing and large-scale transport of the smoke from the fires into the urban airshed. If we focus on relative humidity up in the top left, that has a negative influence on predicted PM2.5, but interestingly, it's much more linear at lower relative humidity levels, and it gets very steep at about 70% humidity. So we're just looking at Swat-Glenori here, but again, that was a very similar result across the different sites. If we look at wind speed on the bottom row, there you're getting an interesting curvilinear relationship. Essentially, at lower wind speeds, it's got the sort of influence on predicted PM2.5 that you might expect. The winds are diluting the pollution, transporting it away from the sensor. But interesting, that relationship switches sign to being positive at about 1.5 meters per second at most locations, not just Swat-Glenori. And we think that changing sign is representative of increased advection of smoke, long distance transport of smoke in from faraway fires. So that's just a brief overview of some of the key findings from this work. And really, one of the key findings was, yes, black summer wildfires had citywide air pollution impacts, but critically, the onset, duration, and severity of those showed really complex patterns of spatial temporal variation. And often that reflects an interplay between the local meteorology and long distance transport by different synoptic features, particularly prefrontal troughs. That was one of the most important synoptic features that has an influence on PM2.5 during this period. Now, all the meteorological predictors gathered by the SWAC and DPIE sensors have generally non-linear influences, but it's interesting how the sign of those associations can change. And we saw that, for instance, wind speed, where the sign shifts, switches at higher speeds, which is indicative of that increased advection of smoke. Now, it's really just the first step, this sort of study, but we do think that the sorts of findings it's producing can help inform future fire resilience planning, can potentially be an input into an early warning system. And that's particularly in regards to the lower cost sensor network that we set up in the schools. So really the study has shown how they can complement the government networks and provide useful data at local scales for citizens that are living in an area that doesn't have a meteorology sensor from DPIE right in their neighborhood. It's right in their schools. So I just want to thank the funders of the SWAC project, which was the Department of Industry, Innovation and Science. You can get the data from our website. DPIE have excellent air quality meteorology data. The website for that data is there. Please do check that out. And then also this work is in Atmospheric Environment Journal if you want to check it out a little bit more. Okay, I'll move on to the final stage now of the presentation, which again is looking at a different sort of data set to look at climate change, look at projections of extremes, and potentially to inform mitigation planning for these events. So it's the regional climate modeling that is being done by DPIE, and that is the NARCLIM project, which I'll now give a brief introduction to. So really this is fitting in with a numerical modeling approach where we're using models to look at the past, present, and future climate. And really, we're in for much of our history as a human species, we've not been able to tell the future. And climate models are our best tool for doing that when it comes to the changes that we want to try to understand. So just to give a flavor of the sorts of projections that we can get from models, one of the main tools is the global climate models, the GCMs, that across the entire globe. And here you can see projected changes in temperature by 2090 under two different scenarios of CO2 emissions. So essentially in the top map there, if those emissions drop to 0 by 2080, under that scenario, then we're looking at changes of about 1 to 1.5 degrees across most of the globe, which is much more manageable than the situation below that, where CO2 emissions have trebled up to 2080. So there you've got much, much warmer changes. So this is the sort of output that we get from global models that are run by CMIP and so on, are very, very useful for looking at a global scale and getting that global information. But living here in Australia, and particularly in Southeastern Australia, those global models are too coarse spatially for us to really make usable regional climate change projections and generate the sorts of data that decision makers need to study the impacts at regional scales. Ultimately, climate change is experienced at regional scales, and that's the scale at which decisions are made to mitigate and to plan for climate impacts. So essentially, we have to take the global climate model and dynamically downscale it. We've got to take that the low resolution data from the global climate model, and we use a regional climate model, an RCM, to dynamically downscale it. And you can see that there in the graphic, a representation of that. You've got very coarse, sort of low detail changes in the globe, and that becomes much more nuanced and detailed over Europe, as an example, when we do the downscaling with the regional climate modeling. And so that is what NARCLIM is all about. It is all about using regional climate models to take the global climate model data, which is useful at the global scale, and render it locally relevant, especially for decision makers. So to give you an overview of the current generations of NARCLIM, we have two iterations. We've got NARCLIM 1 and NARCLIM 1.5. Now, they have two sets of data, each of these. One is very broad scale across the whole of Cortex Australasia. You can see that represented in the map there, and that's at 50 kilometers resolution. But also they have what we call an inner domain, a smaller set of projections over the whole of a large area of Southeast Australia, which is about 10 kilometers resolution. So that captures all the capital cities you can see there, and we've got 10-kilometer resolution data over that area. So each of the NARCLIN generations is run by different numbers of global climate models and producing different suites of data, which you can see represented in the table there. But to look at that in a little bit more detail in terms of what you actually get out of these regional climate models, essentially a suite of 50 plus variables of all the sorts of types that you might need for scientific inquiry of regional climate change. So precipitation, temperature, humidity, wind speed, surface evaporation, evapotranspiration, all these sorts of variables that are useful for looking at climate change impacts, even in an urban region, are being generated by both NARCLIN 1 and NARCLIN 1.5 at 10 kilometers resolution over southeastern Australia. So to look at the sorts of that data that produces, this is a graphic showing that. In the left panel, we've got observations over southeastern Australia at 5 kilometers. So quite a detailed picture there of the changes. And then the next panel shows you how that looks in a global model. So you've got that very sort of simple view of changes in precipitation over that area. You can see there's not much detail, not much spatial variation. But when we look at the regional model, at 50 kilometers of the type that NARCLIN produces, you can see a much more nuanced view of the variation in precipitation. You've got higher precipitation over the topographically complex areas like you'd expect. And then when we go to the highest resolution of data that we produce with NARCLIN, at 10 kilometers, you've got a much more detailed view of the spatial variation in precipitation. So it's that higher level of detail from this data that can be a useful input into the sorts of studies that we all want to run. To give a flavor of that, research that is being done, NARCLIN 1 and NARCLIN 1.5 data is currently being used to look at all sorts of changes, like changes in forest fire danger indices. And so remember here, we can project forwards to 2100 for how quantities like FFDI are going to change. We can look at snowfall changes, different incidences of East Coast lows, very severe storms, urban land use and heat. So all this very useful data is already available. And in particular, that can make contributions to climate resilience planning in many different ways that might be relevant to the audience today. So just to give one quick example, this is future projections of a number of days over 35 degrees over southeastern Australia. So again, this is a 10 kilometers resolution. The top left map shows you the present day situation using observations. And then the next one, panel B, is what the model looks like for the present day. When I say the present day, it's a historical period of 1990 to 2009. So you can see it's not too bad in terms of numbers of days over 35 degrees. But then when we look at what the model is projecting for 2060, 2079 in panel C, you can see this increasing number of days over 35 degrees. And when we subtract the future from the past to look at how the change is happening, what is the delta, you can see an increase of about 1.5 days on average over most of southeastern Australia, along the coastline at least, for these very, very hot days. So it's this sort of information that is currently available from NARCLIN 1 and NARCLIN 1.5 that we're now improving NARCLIN 2. And that's what I want to talk about next, which is the next generation of climate projections. So NARCLIN 2 is trying to systematically improve upon each aspect of NARCLIN 1 and NARCLIN 1.5. And I'll give you a brief overview of some of the new design features. I can't go into all of them, but essentially we ran a user-centered design to try and get an idea of the sorts of functionalities and improvements that people wanted to see in NARCLIN 2. And one of the main ones, which I think is going to be really very, very useful, is higher resolution simulations. So the outer domain of the Cortex Australasia will be at 20 kilometers resolution, but importantly, that inner domain over southeastern Australia is going to be at 4 kilometers resolution instead of just 10. So if you can imagine the greater level of detail that will give climate adaptation planners looking at things like heat waves or protracted periods of droughts, you're getting much more level of detail from a geographic perspective when you've got those 4 kilometer projections. Another thing that we're increasingly hearing from users is essentially to use a larger number of the latest global climate models to drive NARCLIN 2. And that's really to get a broader diversity of the range of future climate projections. All the models have different levels of warming or drying or vice versa. And we just want to get the breadth of those to a slightly better capacity. We're already doing a good job of that when you combine NARCN 1 and NARCN 1.5, but to be able to capture that change in a little bit more detail would be useful. Users want a fuller consideration of climate extremes. This completely, makes a lot of sense. And when they say fuller consideration, obviously we're already generating a lot of climate extremes outputs from NARCN 1, NARCN 1.5. What they mean is they want us to make sure that NARCN 2 does a particularly good job of simulating climate extremes, which makes a lot of sense given the impact they have. They also want improved accuracy of general simulation outputs, so particularly temperature and precipitation, some of the basic variables that you would need whether you're looking at the urban heat island effect on one hand, flooding on the other. That's just an overview. There are other improvements as well that are being made, but essentially the design approach to NARCN 2, which is a big part of the work I'm doing, is to make sure that we select the most accurate and independent latest GCMs to drive the regional climate modeling process. And also when we're designing the regional climate models themselves, to do a lot of testing to make sure that we select the most accurate physics configurations that really do a very, very good job of simulating the Australian climate. So to deliver what the users are asking for, the better representation of climate extremes than the current technology is able to do. And then also to make sure that the models capture the full range of future climate changes. So to just give an idea of the sorts of rigor and detail in the evaluation of the models, to make sure that we select those that do a really good job of simulating the climate, we basically evaluate how well they can simulate many different aspects of the Australian climate, from the very basic in terms of mean precipitation, mean temperature, to actually specifically looking at how well they simulate extreme climates. So for example, there are the ETSI extreme indices. So again, it's a little bit like the map I showed you, looking at how well the model can do something like simulate count of days with precipitation above 10 millimeters relative to observations, and to pick the models that do a good job of simulating phenomena like that. Also looking at things like climate modes. So for example, El Nino, La Nina, looking at how well models can simulate those phenomena, because that has an effect on how well they simulate precipitation. So that's the sort of process that we're going through with NARCN 2. And to give an example of how that looks, these are the evaluation results for the different GCMs. I've boxed in red the models that do a really bad job of simulating the Australian climate, either because they're far, far too overestimating of temperature, they're warm biased, which are the maps where you're mainly seeing red, compared to the models that are far too cold relative to reality, which are the models that have predominantly blue, intense blue over Australia. So we're getting rid of those models and just focusing on the best ones that we can use to drive NARCN 2. I mentioned as well, we need to have physics testing to ensure that the RCM has the best possible configuration possible. Again, this helps the model give an accurate simulation of the Australian climate. So we've done very rigorous model testing that I've led the work for NARCN NARCN 2, and that really builds on the work that was done for NARCN 1 and NARCN 1.5. Those early iterations looked at 36 different physics tests, whereas now we've done 78 different physics tests. So we've built on that. That's actually work that we did in concert with UNSW, so that was a joint effort, but we've really expanded the amount of testing that we've done. And really that's to try to reduce the errors that the models generate, because they have this tendency to either overestimate or underestimate critical variables like precipitation and temperature. And to give an example of how that looks, these are the results from the physics testing. It's sample results. Here we're just looking at temperature errors across southeastern Australia. And I said we've done 78 different tests. Here the maps just show you the ranks of the models from the bottom ranked model, rank 78 up in the top left, to the top ranked model, rank 1 in the bottom right. And we're incrementing in steps of 10. And if you look at the top panel there, or the top row, you can see these really strong widespread errors in the models where they're strongly blue because they're really underestimating the temperature very, very badly. And here you've got errors of about 2 to 3 degrees. But then as we iterate forwards to the better performing models from our testing, if you look at rank number 1, here you've actually got really low error. You've got error of about half a degree, which is much, much better than we have been able to achieve in the past. And this is using some of the latest model configurations that I mentioned. So overall, NARCLIN 2 is what we're working on right now. Accurate performance than previous iterations. We're running the simulations now, and we think that the first series of results are going to be ready by mid next year. So please do keep an eye out for that. It will be coming very soon. But right now, you can obtain NARCLIN data and outputs from two main sources. There is ADAPT New South Wales, the URL for which is up on the left there, and we have recently developed a new climate data portal for everyone to get free access to NARCLIN 1 and NARCLIN 1.5 model output data. Highly usable and very, very good for looking at things like urban heat island, pollution impacts, and different changes associated with climate. Thank you very much for your attention, and also for giving me the chance to present some work today.
Thanks very much, Giovanni. That was really, really interesting. I really enjoyed that. I wanted to open it up to questions to the crowd. Sorry, I just realized my video is not open. There we are. I did want to open up to questions to the crowd. We don't have any in the chat at the moment. So if anyone does have a question that they wish to ask, I'm opening up the floor.
Go on, Chris, sorry.
Thanks for the talk. It was really fantastic, Giovanni. Just wondering with the SWOC data and using they're not that low cost a device, I believe, but and you presented data for where you compared the SWOC data to DPIE data, and I noticed that especially for the bushfire periods, I mean, there were extremely elevated levels of PM 2.5, up to 100, 200, 300. The sensors were really good at picking up those highly elevated concentrations. I'm just wondering, the perennial question is, how good are these devices at looking at the sort of ambient levels that we normally experience? So I'd just be really interested in getting your thoughts on that, and also seeing, for instance, if you ran agreement statistics like Bland-Altman type statistics as well. I'm just involved in looking at a different type of sensor and data from that different sensor, and would love to get your thoughts. Thanks.
Thank you. Thanks for that question. It's a good question. So my impression for these particular sensors for that study period is that they do a much better job of capturing ambient pollution rather than extreme pollution events. But there was deviation between the low-cost sensors and the regulatory grade sensors that was much more sharp and really quite substantial when we had the bad air quality days of Black Summer. But then during normal life, they're actually much more accurate. But notwithstanding that, the SWAC sensors were still able to register the pollution events that were being picked up by the DPIE sensors. So really, it's about often financial considerations and pragmatic considerations wherever you want to go with these sorts of lower cost sensors. And really, we found that they were pretty useful for expanding our knowledge for these areas that were outside of the DPIE network. And for all intents and purposes, using them in concert with the government network, using the government network as like a sanity check, if you like, of the lower cost sensors, seemed to work out really quite well. And if you had more sensors in your network, which we're trying to do, both at DPIE and SWAC, then you can start to use the regulatory grade sensors to scale even the lower cost sensor data that's coming out. But yeah, overall, to answer your question, throughout most of the year, they do a pretty accurate job, but you did see bigger divergences between the government sensors and the SWAC sensors when you had these really high concentrations of PM 2.5.
Okay, thanks.
Thanks.
Cool. So Jeff, I think you had a question as well.
Yeah, look, thanks, Giovanni. Unfortunately, I missed a bit of the presentation, so excuse me if you've already covered this, but with NARCLIM, you do projections into the future, and those projections are daily projections. Is that right?
We do projections at various timescales. So we go down to
that include daily, yeah.
Yeah, they do definitely include daily, and they go right down to hourly for core variables, and then up to monthly and seasonal for others.
This is a sort of difficult question to answer, but some of the health risks that we look at are related to short-term exposures, like daily exposures. And if we're looking at, what happens into the future, we're applying sort of health risks to those daily values. Sometimes, years into the future. How do you judge the confidence and the performance of models around daily variability? And is that the same as sort of annual variability and all that?
Yeah, it is. We evaluate the models at the daily timescale versus the best observations that we've got. So typically those observations produced by the Bureau of Meteorology, and they've extrapolated observations from stations across a large area like Southeast Australia. And so we essentially compare daily temperature from the models for a historical period with daily temperature from the observations and gauge the level of bias or error in the models. And that's really fundamental to being able to let users know what are the limitations of the model data. So typically you are getting models that do a pretty good job of capturing the observed mean of the distribution, but where they tend to struggle a little bit more is at the tails. And so that's one of the things that we're trying to improve with the latest generation of NARCLIM. But nevertheless, yeah, we do evaluate for those sorts of model behaviors at daily timescales.
Thanks.
Very cool. Do we have any other questions from anyone? If not, I've got one. So Giovanni, now that NARCLIM 2 is kind of on its way, are there plans to? First part of the talk, you talked a lot about how you could tie some measures of air quality with synoptic types and other meteorological variables. Are there plans to do something similar with that with NARCLIM data, or is that something that would be possible?
That is something that would be possible, and that is definitely something that I would love to have the time to do. Myself, I don't, but other people can do that. That is totally possible to do. You can do that with the current versions of NARCLIM. Because of the high resolution, it will be even better to do that with NARCLIM 2. But yeah, you can do that right now, and that data is really available. And so we're perfectly happy to also talk with users about what they're interested in doing with the data. But that's a good idea, and that is exactly the sort of thing that you can investigate.
Yeah, very nice. I'll give it another minute for any questions if anyone else wants to speak up. Alrighty, well, in that case, thank you very much, Dr. Giovanni Di Virgilio, for that. That was a really interesting presentation, really enjoyed that. So thanks, yeah, really, from all of us here at CAR, thanks for giving your time to present that talk. And yeah, hope to hear from you again soon.
Thanks very much for inviting me. I really appreciated the chance to talk today. Thanks again, everyone. All the best.
Thank you.
Bye.
Yeah.